In previous lectures, we introduced our polarization bases, our three complementary bases, the HV bases, the plus minus bases, which we sometimes call PM, and the RL bases. We also introduced the observables, operators, for the HV bases that we're going to call Z, which is 1 minus 1 on the diagonal, X for the PM or plus minus bases, off diagonal ones, and the RL has I's in there, as we talked about in the previous lecture. And these are the observables for those particular bases. We call them X, Y, and Z because they originally came from the spin directions, which were, think of X, Y, and Z as perpendicular directions with spin. But the Hilbert space structure is identical here for polarization, so the physical mapping is different. Now, let's look at some examples, and we want to kind of look at the state vector as it relates to these. So we'll just take a look at the H vector, the horizontally polarized photon. Again, we're not paying any attention to the momentum or energy of the photon, just its polarization state here as we analyze this. And we said that the H is an eigenvector of Z with eigenvalue plus 1, because obviously if you take this matrix and act on that, again, we're representing this in the canonical form where H and V are a canonical basis, you get 1 times H back. That's what we mean by an eigenvalue. Now, it's clear, should be clear, that the plus, which is this case here, is not an eigenvector of Z, because again, if you map this onto this, you get 1 minus 1, and 1 minus 1 is the negative ket. So what the Z does is it changes the plus ket into the minus ket. So it's not an eigenvector, and the action of Z on it changes the state. Now, the importance of this is that the eigenvector in that particular basis, it's in a definite state. So we say that in this case, the photon really, we can say there's an element of reality that the photon has horizontal polarization in the HV bases. Another way to say that is if we measure in that basis, the HV bases, we're going to get the corresponding outcome with probability 1. And we can say, it goes back to Einstein or 1935, that we can associate then an element of reality, if we like, to that photon because it's an eigenstate. It's an eigenvector of that operator in the HV basis. Now, because the plus is not an eigenvector, we can see that when we either measure a particle, now in a photon we usually destroy it upon measuring. A spin you don't have to, but or just projecting, which we talked about before. If we project along one direction, it affects the other basis values. So as an example, let's consider this carefully. Let's take an H state and pass it through a polarizer that's orientated along the minus direction. So that would mean that, let's make a picture of this. So if we have, say, a photon coming in that's definitely H, and it impinges on a polarizer, we'll kind of represent it like that, which is in the minus direction. That's what we mean by that. It's rotated by minus 45 degrees, if we want to say, or 45 degrees in the, as defined previously. What passes is projects out the minus state, so that means after that polarite is definitely in the minus state. But if we actually carry out a measurement there with a polarizing beam splitter, and we put photodetectors there, where this is, say, this one represents H, again that's a PBS, polarizing beam splitter. This one's a V. If we do this over many runs, these two will flash equally 50-50, which means that the HV value, which we started with a definite value of H, plus 1 if you like, once we transformed it by passing it through the polaroid, projected out the negative component, if you will, we've kind of destroyed or erased, if you will, that distinct property or that unique property it had of being H. So we can't have it to be minus and H at the same time. And again, that should be clear from the ket structure as well. So again, projecting along H and then along minus direction disturbs the original HV value. It no longer has a definite value in the HV bases, so here it has a definite value in the HV bases, here it has a definite value in the PM bases, but not the HV bases. And then when we do the final measurement, well, that just kind of determines which one the final one's measured. Okay, so we're going to go a little further with this and analyze this state. So let's take this h, and again, pass it along the minus direction. But we want to look at this in terms of the operators a little more carefully, and we want to make a construction here. So let's consider the following. Let's take the h state and act on it with the z and the x. And let's see what we get. And if you think about this, so just you can look back, but it should be obvious now that h was an eigenstate of z with plus 1, so this just collapses, this combination z on h just becomes h. Then x on that, and we said the x is the swap operator in the HV bases, so we end up with v. Okay, that's fine. But here's what we want to do. We want to consider the reverse order. So we want to take x on h, then z on h. So we act on x with h, and that swaps it into a v, and then z acts on it. And remember, v is the eigenvalue or eigenvector of z with eigenvalue minus 1. So we end up with a different result. And this is the way we tell that one measurement or one action of one operator affects the other. Now, we want to be careful here. And we want to be explicit here, and so take note that the act of operating on a state vector is not a measurement. That's not equivalent to a measurement. And the reason is because if we recall postulate 3, quantum mechanics, through the Born probability rule, only gives us probabilities for outcomes. It doesn't tell us which one it is. So when we act on it with a operator on a ket or a state vector, that is not a measurement. And again, as we said, there's no algorithmic way to determine the outcome within quantum mechanics in general. Unless it's an eigenstate and we know it's in that eigenstate, then we can say, yeah, it's probably one that's going to occur. But if it's in, if it's not in an eigenstate, then there's probabilities associated, and we don't know which one we're going to get, but it's going to be in accord with those probabilities. So we want to kind of expand on this order of the operators here. And so what we're going to do is make a little theorem here. We want to consider a state. Now we're going to be general here. We're not necessarily talking about polarization, talking about anything, really. But we want to consider a state, we'll call it AB, that is an eigenstate of two distinct observables, A and B. And those are Hermitian operators, so we have real values coming out. What does that mean? Well, that means if we act on AB with the operator A, it returns the same ket, because it's an eigenvector, and it has the eigenvalue A. We're labeling A and B as the eigenvalues. So it just, A comes out. That's what our eigenvector-eigenvalue connection tells us. But if we take the exact same state, and we act on it with B, we get the B eigenvalue coming out. Okay, and that's what we mean by it's simultaneously in an eigenstate of A and B, of the observables A and B. Now let's take the different orders. So we're going to make the following construction. We'll take this operator, AB minus BA. And let's see what the action of that does. So here we go. So that's going to act on AB. And we'll do them separately. So let's just consider this one. This B operator acts on this, giving us B. And then A acts on it, giving us AB. In this case, A acts on it first, giving us A. And then B acts on it. But B acts on that, gives us little b. So we just get AB minus BA. And again, these are scalar numbers, so they commute, so that this vanishes. Now, this notion, or this operator, if you will, this subtraction of them in different orders, is of utmost importance in quantum mechanics. It's one of the most important things. To Dirac was probably he said it was the central thing defining the difference between quantum mechanics and classical physics. So what we mean here is that if a state has definite values of two distinct observables, meaning it's an eigenstate of two distinct observables, meaning it has a value A and it has a value B at the same time, then the operators vanish essentially. And again, we call this construction the commutator, and it's defined as follows. We use this bracket notation, just a bracket with A comma B. It's order dependent, remember, so if your BA is not equal to AB, obviously. And it's just the difference of the operators in the opposite orders. And what we just found if the commutator of two observables vanishes, then those two properties can be simultaneously known. You can do a measurement of A, you can do a measurement of B, you can do it in any order you want. It doesn't matter. You'll still get, so again, if in this case, if we keep measuring A several times, or B, A, any order we want, because neither B or A changes the state, we're just going to get the values A and B out corresponding to whatever measurement we made. In that case, we say the observables are compatible. And you can know them at the same time. Now, in the case where the commutator does not vanish, that's really the interesting one, then the two observables cannot be known simultaneously. And we call those incompatible observables. And again, this is an entirely quantum phenomenon. In classical physics, all observables can be known simultaneously in principle. There are some, statistical mechanical discussions, but in principle, you can know everything in classical physics. Another way to just say that in classical physics, all observables commute. That would be another way to say that. Okay, let's go back and let's look at our polarization. Are the polarization observables compatible or not? Well, you should probably already know the answer to this, but let's go through it. Because we showed earlier, remember we talked about X or Z acting on H, then X acting on H, we got V, and then we did it in the reverse order, we got minus V. So if we construct a commutator in this case, we get XZ on H is equal to 2V, which is not equal to 0. Now again, you can also go back, and I urge you to do this, go back to the matrix form and determine the matrix commutator, the commutator as a matrix, by multiplying the matrices in two opposite orders and subtracting them. You'll find it's not equal to 0. It's non-zero, which means that the X base, the HV and the PM bases are incompatible. You can't know them at the same time. So you can't have a simultaneous property of HV polarization nor PM at the same time. Now, you can go through quickly with those matrices and show that these three bases are mutually incompatible. And this, again, this coincides with what we've been saying. The reason we chose these as complementary bases because we said if we know in one basis, we have no idea what it is in the other because it's 50-50 the outcomes. So it's consistent with that. Now, we can also, so we did this in terms of polarization, but remember the Hilbert space structure is the same for spin 1/2. So for a spin 1/2 object, we can take the measurements along X, Y, and Z being the mutually incompatible bases. And those are complementary bases as well. Now, it turns out there's other incompatible observables, and you probably heard of positional momentum as an example, direction of angular momentum in the X, Y, and Z direction. One that's a little bit not stated usually in this way, but it's which path information and interference pattern in a double slit. You can actually come up with a way to determine that. You can say how much which path information you have. If you have which path information, you do not have an interference pattern and vice versa. There, it's a little bit more gray. Well, actually, all of these are, well, positional momentum and which path information, it's kind of a scale. It's not either yes or no completely. Because again, here, if you know an HV completely, you have no idea what it is in the other one. Here, it's like there's a trade-off between the two, between positional momentum and which path information interference pattern. We'll get that in a later lecture.